going to give everybody an extra couple of minutes since we need this consent to record. I just want to make sure everybody's in and has agreed, and it looks like everybody except for Vanessa, who just got here, has already done that. So just a couple of minutes. Awesome. I want to make sure that nobody else joins. I'll give it like 1 extra minute just to make sure we don't have any latecomers, and then we'll move on. Fair warning, Mike, you might be a little bit bored. I recycled some of what I used in my makeup sessions that you came to, so we'll be doing that same limiting reaction problem, but then we've got some time afterward to work on just kind of some individual stuff. So if nothing else, you will be really, really, really proficient at limiting reaction problems. I think this is new to everyone else, but if you've already done it with me, just be patient. We'll get through it, and then we'll work on some new material when we're finished. All right, I put a new page up. If y'all will just look through it, read through it, think about anything that you might want to work on in addition to limiting reaction problems. Look through your book if you want, try to pinpoint something that was difficult for you. Obviously, with 9 people, we might not get to every single thing, but often it's the same thing that people are having difficulty with. So think about anything that you might want to go over, and I'll try to collect that and add an activity in at the end, and then we're going to go ahead and get started with some limiting reaction problems. Okay. So balancing equations. Jennifer, can you find for me what chapter, or if you know what specific section that information is from? Or if anybody happens to know about where that was. So I know what you're talking about, but I don't know exactly where to find that in the book to find some problems that would help you. Well, while I give you guys some time to work through the first couple of problems, I'll flip through the book and see if I can find some specific information. just writing the formulas for the compounds. Okay. Okay, cool. We'll start with limiting reactants, and if anything else pops up when we finish that part, just ask away, and we'll try to get this figured out together. All right. So I know at least one of you has done this already. I added some sessions because of the snow days and used kind of a mix of my material from last week and from this week. So if you've seen this already, then just work it out by yourself. Make sure you can do it quickly. Make sure that you know all the steps without thinking about it too much. Oh, okay, chapter 6, 6.3. Got it. Thank you. Okay, so this limiting reaction problem, again, I apologize to those of you who have seen this or done this already. This one is actually particularly easy, and the reason it's really easy, well, a few reasons it's really easy. One is that right here we already have a balanced equation, and it doesn't always just give that to you. Sometimes you're going to have to write your own balanced equation, and you're going to need it in your calculations, and you'll see why. Another reason it's easy is because it says that it's a limiting reaction problem, and not all limiting reaction problems say that they are limiting reaction problems. Like in the harder one that we're going to do next, you'll see how you have to read through it and determine what it is and what to do with it. And then it's also easy because we don't have to do anything with converting grams to moles in this situation. We will in the next one. But this one, all it's asking is for us to determine the limiting reactant. So we don't have to calculate the number of grams we can make. We can just calculate the number of moles, and then y'all remember from class that when we are deciding which one the limiting reactant is, the limiting reactant is the one with the smaller number because it limits us in how much we can make. You can't, you know, like the peanut butter and jelly sandwich example, or the peanut butter sandwich, if you only have 20 pieces of bread, but you have 1,000 pounds of peanut butter, you can still only make 10 sandwiches. It doesn't matter how much peanut butter you have. The bread is your limiting reactant, and 10 sandwiches is all that you can make because of that. Okay. So our first step here, we're going to do A, and we're going to have to calculate these two things separately. Whenever you see a limiting reaction problem, what you're going to do is you're going to first look at what you're given, and we're going to calculate these things separately. So I'm going to draw a line down the middle. We're going to first calculate with 3 moles of N2, how many moles of NH3 can we make? And then separately, we're going to calculate with 5 moles of H2, how many moles of NH3 can we make? And then we're going to choose the smaller number. Simple as that. So you can do this on your own if you would like. If you've done this before, if you're very familiar with it, go ahead and just do it. And you can type in for A, which one the limiting reactant is. If you're not exactly sure how to start it, then I'll go through it. And then I want you guys to all do it independently on the second one, and then we'll talk about it. So nitrogen and hydrogen react to form ammonia. We have 3, I'm not going to write the 3.0, but I should. I will scribble in moles of N2. And we need something that is going to get us from moles of one thing to moles of another thing. First of all, what do we need to get to? Moles of what? Somebody type it or turn on your mic and speak it. Yeah, we want moles of NH3. And so we use what we call a mole-to-mole ratio in order to find that. And that's where we look at the coefficients up top, and we just fill in the numbers. So we know that we have to put moles of N2 down here on the bottom because we want to cancel it out. And then we want moles of NH3 up here on the top, because that's what we want to end up with. So right here, our coefficient is 2 moles of NH3. And then there is no coefficient in front of N2. Don't make the mistake and use this subscript right here. We're only looking at the coefficients. And if there's nothing in front of it, then it's assumed to be a 1. So all you have to do is multiply across. 3 times 2. So with 3 moles of N2, we can make 6 moles of NH3. Now with 5 moles of H2, somebody calculate it out the same way for me and tell me how many moles of NH3 we can make from 5 moles of hydrogen. How many moles of NH3 can we make with 5 moles of H2? And then this is assuming that we have just as much N2 as we need. What's the answer right here? Anybody? How many moles of H2 do we have? We look up here and we find it in the coefficient. The 5 moles of H2 is what we're given. That's what we start with. But when we use a mole-to-mole ratio, we always get those numbers from the coefficients. So we got this 2 from up here, because it's 2 NH3. Up here with this 1 mole of N2, we got the 1 because there's no coefficient in front of N2, so it's assumed to be a 1. And then when we do the 5 moles of H2, then we use a very similar mole-to-mole ratio to get from moles of H2 to moles of NH3. And so we take that same 2 moles of NH3, that number goes here. And then there are 3 moles of H2. That's why the balanced equation is so important. And then that's 3 moles. This is moles. That 3 moles of H2 is very important. So then we take this equation, we do the same thing with it. We would take, in my calculator, I would hit 5, and then in parentheses, I would put 2 divided by 3, close the parenthesis, yep, and we get 3.3. 3.3-ish. Okay. So which one is our limiting reactant? Yeah, H2. Because we could make a lot more with that many moles of N2, but we don't have enough H2 to do that. The H2 is what limits us. It limits us to only be able to make 3.3 moles of NH3. So that is our limiting reactant. So do the same thing with the smaller one. Take a pencil and a piece of paper and set it up just like this. Start with what you're given. calculate them separately. Make sure your mole-to-mole ratios are accurate using the correct coefficients. And see if you can come up with not only which one the limiting reactant is, but how much of it can we make. When you work it out and you've got an answer, just type it into the chat box or turn on your mic and speak if you want. So Vanessa says you can make 16 moles of NH3 with 8 moles of N2, and that you can make we'll call it 2.7, he means 2.7 moles of NH3 with 4 moles of H2, which makes H2 the limiting reactant. Do me a favor, if you agree with that statement, up above the list of our names, there is a little check mark box. If you agree with that statement, choose the green check for me. If you are unsure or if you disagree, choose the red check. Let's make sure we're all on the same page. Waiting for a few more. If you guys need another minute to work it out, you can. If you've got a question, now's a good time. It's a participation grade, so make sure you get a responses. I haven't gotten a response from Selena, from Samira, or from Tilly. I'm going to go ahead and move on, but we're going to have a similar thing in a little bit, and you guys need to make sure that you're participating. Okay, so we're going to do something similar, and this one is much more difficult. So we pointed out in the last one that those limiting reaction problems were easy. They're easy because they say they're limiting reaction problems. They're easy because you don't have to include grams in your calculations. They're easy because they come with a balanced equation. This one comes with none of that. So we already know that we're going to need a balanced equation in order to use the mole-to-mole ratios. And we know that we're going to have to do some extra calculations because we have grams here and not just moles. So the first thing we're going to do is write a balanced reaction. And that seems kind of hard, but if you read through what the problem tells you, it should be pretty easy to write it. So what this says to me is when sodium and chlorine react, they make NaCl. So I'm going to write it out, and then we're going to try to balance it. So Na plus Cl2 makes NaCl. But you can already see that it's not a balanced reaction. So show me what coefficients I need. Type it into the chat box, just 1, 3, 4, or whatever. What coefficients do I need in front of each of these? Good. So we can see that we have 2 chlorines on the left side and only 1 on the right. So when we correct that and place a 2 in front of NaCl, then we have 2 sodiums on the right and only 1 on the left. So we place a 2 in front of sodium, and now we have a balanced reaction. So if you are given this problem and given this equation, you should always check it to make sure that it is balanced. You should assume that any equation you see on your exam is not balanced. Just always check it just in case, because it'll make your calculation wrong if you don't put those 2's in front of them. So how do we start with this? What do we need to calculate first? Any guesses? We need to know how many grams of NaCl are produced. Yeah, grams to moles. So remembering that we're doing these one at a time, we're going to focus on 12.8 grams of sodium. We're going to do that first. So what Mike said, it's grams to moles. So we need to start with what we're given, 12.8. So how do we take this 12.8 grams of sodium and change it to moles? So what Jennifer, if everybody read that, is referring to is using the molar mass from the periodic table. Anytime you go grams to moles or moles to grams, we do that by using the molar mass on the periodic table. And so the molar mass of sodium is 22.99. I'm gonna write 23 because it's easier to write because the 10 is difficult. But don't round it unless you know that it's okay to round it. Always use the exact number. So grams of Na, because we want to cancel out grams and get to moles. And then up here we're going to have moles of Na. So 23 is what I'm going to write down here for 22.99. And then what number do I put on the top for moles of Na? Good. Yeah, it is 1 and not 2. Don't make that mistake. It's 1 because molar mass is defined as grams per 1 mole. So anytime you take something off the periodic table and you use that mass to convert from grams to moles or moles to grams, it's grams per 1 mole. And so in this situation, it'll always, always be 1 mole per 23 grams. We use the coefficients when we do a mole-to-mole ratio, which is what we're going to do next. So a mole-to-mole ratio, molar mass is how we get from grams to moles. Mole-to-mole ratio is how we get from moles of one element or compound to moles of another element or compound. So we don't want Na because it's asking for grams of NaCl. So we're going to use that mole to mole ratio just like we did in our really simple problems to get from moles of Na to moles of NaCl. So what numbers go in these guys right here? Moles of Na is going to be on the bottom. Moles of NaCl on the top. Yeah, simple. 2 and 2. Get those from the coefficients. So now we can find out how many moles of NaCl we can make, but that's not what the problem asks for. The problem asks for grams of NaCl. So what is our very last step? Why is it 35 grams of NaCl? Where did that number come from? So chlorine is 35.45 grams, and sodium is 22.99. So we get 58.44. 58.44 is the molar mass of NaCl. So in grams right here, it would be 58.44 over 1 mole, because it's molar mass. So how many grams of NaCl can we make from 12.8 grams of sodium? Anybody calculated that out? No, try that one again. It should be a little bit bigger number. My calculator, I'm putting in 12.8 divided by 22.99. I'm not going to do the times 2 over 2 because it's redundant. It's just 1. And then I'm going to do multiplied by 58.44. And yep, we need 3 significant figures because 12.8 is 3, 10.2 is 3. So 32.5 grams of NaCl is what we can make from 12.8 grams of Na. So what's our next step? Is this our answer, 32.5 grams? Are we finished? What do we need to calculate next? So you have to go. You could do it either way, Vanessa. That's just the way that I do it. You could hit 12.8. You could multiply everything in brackets. You could multiply in brackets 1 divided by 23 times, in parentheses, 2 divided by 2 times, in parentheses, 58.44. You can multiply all the way across the top and then divide all the way across the bottom. There are a lot of ways to do it, but make sure that you can put this into your calculator and end up with 32.5, however it is that you want to do it. So you can do 12.8 times 1 times 2 times 58.44 divided by 23 divided by 2 times 1, and you should still get 32.5. The answer isn't dependent on the coefficient, Mike. It is, I don't know how to explain this. It is there because this is how the reaction is balanced, but it's not Na2Cl2, it's just how much NaCl. It wouldn't ask how much to NaCl, it would just ask how much NaCl. We just know that we need 2 moles of Na to react it with the chlorine because the chlorine is a diatomic element, so it has to be 2 of those, and then we just need this 2 in order to balance our reaction. We know that we need to have 2 moles of this for 1 mole of this diatomic element. You're never going to calculate for 2 NaCl. It's just one of those things, it just is. All right, so the next thing we need, because 32.5 isn't our answer, we're only half done. We haven't done anything with this 10.2 yet, grams of chlorine. So now, remember, in any limiting reaction problem, first we write the balanced equation, and then we have to do our calculations for each of these things, and they have to be done separately. So our next step is to go through. We're going to use a lot of these same numbers. Obviously, the molar mass of Cl2 is different. We're going to use different mole-to-mole ratios because we're going to use the coefficient from here. And then the molar mass at the end, the NaCl, is going to be exactly the same. So we're going to start with what we're given, which is 10.2 grams of Cl2. And what's the next thing we need? We need to get from grams to moles. So think about this carefully. In 1 mole of Cl2, how many grams are there? What goes on the bottom here? Yes. Do you guys agree? 70.9? Because if I look on the periodic table for the atomic mass of chlorine, it says 35.45. Why can't I use 35.45? Yeah, because that's only for 1 Cl. This is diatomic, so it's Cl2. It's always found in nature. If it's not attached to something else, it's attached to another one of its kind. It's Cl2. Now, why didn't we do that for Na? Why didn't we multiply by 2 for Na when we did the molar mass of it? Yeah, we only do that when it's a subscript. We don't ever do that for a coefficient. That's just something that you've got to remember. If it's a subscript, if it's Cl2, then we include 2 in our molar mass. But if it's 2Na, we don't do the same thing. It's just something that you have to know. All right, so we've got our grams to moles, but we're at moles of Cl2 and we want moles of NaCl. So in order to cancel them out, the moles of Cl2 goes at the bottom. Moles, this little scribble means moles, just so you know. Moles of NaCl goes on top. And so you guys know already, you're catching on really quickly, that we look to our coefficients. So 2 NaCl, because that's the coefficient. What number do I put in front of Cl2? Do I use a 2 or do I use a 1? Yeah, because we're only looking at coefficients right here. And there's nothing in front of it, so it's assumed to be a 1. We never use this 2 as a number in a mole-to-mole ratio. That's just not what it's for. It's just not how we do it. You just got to remember that. So 2 over 1. And then I'm going to use the exact same piece like we did up here, again, because we've already calculated the molar mass of NaCl. You know that it's 58.44. So calculate that out for me. And tell me what you get for this one, and then tell me which one is the limiting reactant. Putting in 10.2 divided by 70.9 times 2 times 58.44. Yep, 16.8. So which element is our limiting reactant? Yeah, Cl2. So the way that this would be asked on an exam, you might do a couple of these more simple ones like we did before. You might have a couple of those. Most likely you're going to get one that looks just like this. And this is in your book. It's 9.51. It's going to look just like this. It's not going to tell you it's a limiting reactant problem. It may not have an equation at all, and if it does have one, it might not be balanced. So it's going to ask you exactly this: how many grams of NaCl are produced? And if you don't know to calculate both of them, if you forget and you only do Na, I promise you 32.5 is going to be one of your answer choices, and a lot of people are going to choose it. How would we solve the remaining of Na? Yeah, some questions, I don't remember if I was asked on an exam or not how much leftover of Na we have, but you would just work the remainder. I don't remember being tested on an exam. Is that a sapling thing? Does it make you do that in sapling? Okay. Then you would, you know that you're only going to make 16.8 grams of NaCl. This is NaCl. And so, it's been a while, but I believe, feel free to stop me if you feel like this is incorrect, I believe we would use our 16.8 grams of NaCl. And we can use that to calculate how much Na we would use. So we would use the NaCl, and then we would use the molar mass of NaCl to get to moles, so the 58.44. So then we would have moles of NaCl, but we want moles of Na. So, so we'd have 2 over 2. So now we're at moles of Na, and we would want to go grams of Na to moles of Na. I'm simplifying this a lot. Are you guys following? You understand what I'm doing? It's the same type of calculation. We're kind of just working backwards. Okay, good. So let's see. This is, that was grams, so this is moles of Na. So which side? I guess I should have done it a little bit more carefully. Okay, this is moles of NaCl, moles of NaCl. This is moles of Na. So moles of Na goes up here. Yeah, you're right. 58 would be down here on the bottom. But you would basically go through the same type of calculation, and you would use mole-to-mole ratios, and you would use molar mass of the elements to go from grams of NaCl, because now you know exactly how much you're going to use. And then you would go through the same process, and let's make up a number. Let's say that when we have 16.8 grams of NaCl, what it's telling us is how many grams of Na we would have to use. So let's say, just for example, that we would use 10 grams. Let's say that's our final number. We would use 10 grams of Na in order to make this. But we have 12.8 grams, so in that case your excess would be 2.8. So it would just take one extra calculation. Does that make sense, or did I mix you up even more? Just knowing the steps in this process of how to get from one thing to another thing is honestly the most important. Being able to get from knowing that you have to go from grams to moles to do anything with this type of equation, knowing how to use mole to mole ratios, and then knowing that you have to get from moles back to grams. Yeah, the excess is the remainder. So you just work backwards from what you just did to figure out how much Na you actually use. So in this actual equation, if we're using 10.2 grams of Cl2, then we're only really going to use 10 grams of Na. The rest of it would just be left over. It wouldn't react. Okay. So you guys asked, one of the questions that we had was about the charges, about combining these elements into compounds and how we know what the charges are. This is something that you should have memorized. So if you've got your book in front of you, on page 180 in chapter 6, there is a really awesome visual. It's just a little piece of the periodic table. And it shows you the charges by group number. So 1A, it's going to be +1. 2A is 2+. We're going to ignore just for now some of those transition metals in the middle because they have variable charges, and that's the most confusing part. But you should know that 1A is always +1. 2A is +2. And then if you skip those transition elements, skip all the B's, don't mess with any of the B's. Get to 3A, and you'll see in group 3A that the charge is 3+. And then we skip 4A, but then in 5A it starts to count backwards. So I would honestly, I would get my periodic table and I would write above group 1A, I would write plus. Above group 2A, I would write 2+. Above 3A, I would write 3+, just to remind myself. And then you see in 5A, we start to go backwards. In 5A, it's 3-. 6A, 2-. 7A, 1-. And so when we look at these things, you know, we talked a lot about NaCl. Sodium is in group 1A, so we know for sure that it has a 1+ charge. Chlorine is in group 7A, so we know for sure that it has a 1- charge. And the idea when we combine these things is to have a neutral charge, so we know that it's just going to go 1-to-1. It's NaCl. Now if we're combining, let's say, hydrogen and oxygen, because that's one that we're all very familiar with. When we combine hydrogen and oxygen, hydrogen is in group 1A, so it has just a +1 charge. Oxygen is in group 6A, so it has a 2- charge. So we know that we're going to need 2 of these pluses in order to make this a neutral element. So 2 H's, the 2 is always a subscript, never a coefficient, and 1 O. You could also, you could look at it in terms of valence electrons, and you know this is what it refers to. I don't remember which exam it was, but it was, you think about the valence electrons, the number of valence electrons in this class quite a bit. The question was something to the effect of like, how many bonds can a certain element make? And if we take O for an example, O is in group 6A. And how many valence electrons does it have? Somebody type it in or speak it for me. How many valence electrons do we have in group 6A? Yeah, we have 6. So 1, 2, 3, 4, 5, 6. So how many bonds can oxygen make? It can make 2. Yeah, it's got an empty space right here where it can make a bond to something, let's say hydrogen. You can bond with hydrogen right there, and it has an empty space right here. You can make a bond. That's another reason why we have H2O. Just a different way of looking at it. You can look at the number of valence electrons. So whatever's easiest for you, I would, just because it's fast, write those charges up above the A groups. And then with the variable charges, let's see, where were we on 180? With those variable charges, you have to look at the charge of the element that you know about, and then that will tell you whether, for example, if you're dealing with gold, gold can either have a 1+ charge or it can have a 3+ charge. So if gold combines itself with, let's say, chlorine, let's say it does that. If it is an even amount, if we have 1 gold and 1 chlorine, chlorine's in group 7A, so we know that chlorine has a -1 charge. So we can look at that. It's a -1 charge. It's equal amounts. So we know that this particular gold must be the one that's just 1+. Because if it was the 3+ gold, we would need 3 chlorines over here in order to make that equal. So there's always a way. It's going to be paired with something that always has a 3- charge or always has a whatever charge. And you're going to look to this to figure out if this is gold 3+ or if this is gold plus, in which case, if you were naming it, you would write it out, gold, and then you would put in your parentheses Roman numeral, either 1 or 3. Is that specific enough? Does that help? Do you guys have any more questions about that? Cool. Yields, theoretical and actual. I can look for a problem to practice. I will say that if you can remember that the theoretical is always the one that we are calculating. We are always calculating. Anything that you calculate is a theoretical yield. In theory, when we put this reaction together in a lab, we're going to make this much of whatever. This is all theoretical. This right here. Theoretically, when we react 10.2 grams of Cl2 and 12.8 grams of Na, theoretically, we're going to make 16.8 grams of NaCl. Now, it doesn't always happen that way, and that's why it's called theoretical, because the actual is what we do in lab. So in lab, you might calculate the theoretical, and then you might do the actual. In an exam where you're sitting down and writing, if something is given to you, if an amount is given to you, little Timmy did this in lab, and he didn't come up with 16.8 grams of NaCl. He actually came up with 17, well, I guess it would be a smaller number, but let's say he only came up with 15.2 grams of NaCl. Something happened. It got lost out there. It got spilled. It whatever. This is the actual. The theoretical is in a perfect world what would happen. The actual is what really happens when you get into a lab. So we're talking about percent yields. Look in your book, or if anybody can remember, what is that equation that we use when we're comparing theoretical to actual? It's on page 293. If you've got your book with you, there's a really great sample problem. It starts on 292, and then there's a really great sample problem if you need to practice it on your own. But what it says is the percent yield is actual over theoretical. So knowing which one is which is important. I'm just going to write ACT for actual over theoretical. So this is our actual, 15.2, because that's what we actually did. The theoretical is the one that we calculated, which was 16.8. And then it tells you to take it and multiply it by 100 because it wants a percentage. So it'll give you the percentage in decimal form, and then you want to multiply it by 100 in order to get it in real form. So you would just take 15.2, divide it by 16.8. I get 0.90476, blah, 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 multiplied by 100. So the answer to this question, hey, little Timmy did this in a lab and he only got 15.2. So what is the percent yield? The percent yield is, I don't know how many sig figs you would need, but 19 point, we'll call it 5-ish%. If you forget which one goes on top and which one goes on bottom, your best like system checker, let's try 16.8 and let's divide it by 15.2. It is going to end up being over 100%. You're never going to yield more. You're not just magically going to have more NaCl than you can possibly make in theory. It's always going to be a number that's below 100. So if you forget and you transpose these and you do 16.8 divided by 15.2, okay, I made 110% of the intended product. That can't be right. So remember that it's actual over theoretical and that it should be a number that's less than 100%, and it'll be super easy to do. So, Mike, I believe it was you that asked in the beginning about balancing equations. Were you talking about when, like what we just talked about over here, when we were putting, the charges, when we were taking the charges and figuring out what it would make? Or are you talking about more like the more difficult versions of what we did here, where we kind of wrote out an equation and then balanced it when we do more complicated things like that? Is that what you were asking for help with? Or did I answer your question already? So more like, I may have done this with you already, I don't remember, but there was a problem that we did in one of the online things. It was a combustion problem. It was C5H10 reacts with oxygen and combusts. And we should know, you should know, by the way, that the products of combustion are always going to be carbon dioxide, CO2, and H2O. You should be able to identify this as a combustion reaction. It's a, think about C5H10, think about that being in a lighter. I've got this lighter and I add a spark and I expose it to oxygen and I get a flame. That's combustion. And then I don't still have this C5H10 floating around. That's not how it works. It combusts and my products are CO2 and H2O in gas form. So that's a combustion reaction. And this one is, it's kind of a pain in the butt to balance, and I'll show you why. There's not a perfect shortcut. You just have to take it step by step. We're going to balance the C's, and then the H's, and then the O's. Whenever you're doing carbon, hydrogen, and oxygen, it's always going to be C first. You should always balance the carbons first. And then usually hydrogens and then oxygens. Sometimes it's the other way around, but always balance your carbons first. So this one's a pain in the butt because we've got to go through a few steps, and you'll see why. So I've got 5 carbons on the left, 1 on the right. I have 10 hydrogens on the left and 2 on the right. I have 2 oxygens on the left, and I have 1, 2, 3 on the right. So we're going to even these out. I'm going to balance carbons first by putting a 5 in front of this. So that gives me 5 carbons. That's now balanced, but it also increases the number of oxygens that I have. So 5 times 2 is 10 oxygens, plus this 1 is 11. Oops. So we see that oxygens are still not balanced, but we're going to go to hydrogens first. In order to make 10 on the right side like I have on the left, I'm going to add a 5 right here. And so now I've balanced hydrogens, I've balanced carbons, and now what the heck do I do with these oxygens? What number could I possibly put in front of this? You can't use partial numbers, you can't use fractions. So we know that we're going to have to do something in order to make this number of oxygens even. We have to have an even number of oxygens because anything that we put in this space is going to be multiplied by 2. So right there, that's your hint that you're going to have to take every single thing right here and you're going to have to multiply it by 2. So we're going to put 10 is this coefficient. We're going to put 10 is this coefficient. We're going to add a 2 here. And then we're going to leave oxygen alone for now because we want to balance it first. So now, how many oxygens do we have? We've got, technically we should go through and we should count the carbons again and we should count the hydrogens again. I'm going to skip that because we're running short on time just to make sure I get through it. So we're just going to balance the oxygens because we already know we've just multiplied everything by 2, that everything else is already balanced. So how many oxygens do we have on the right side now? Take 10 times 2, that's 20, plus 10 more. So we have 30 oxygens. And since we're going to multiply it by 2, we don't need 30, but what we need is 15 right here. And the only way to get through this any faster is just to be able to recognize right away. Yeah, doubling the coefficients is the fastest way out of that problem. You just have to recognize that it's not going to make the same number of oxygens no matter what you do because this was an odd number. This was 11. And there is absolutely no coefficient that you could have put right here that you could have multiplied by 2 and made 11. So, you know, it's like, hey, red flag, I have to make this into a different number. And actually, when you're doing a combustion problem like this, you can see from the very beginning you have an odd number of oxygens, no matter how many coefficients you put in front of it, because this is going to be even. And unless this is also an even number, you can see that you're probably going to end up with an odd number. So just go ahead and balance out the carbons and balance out the hydrogens, and then if you can't do it, just know that the next step is to multiply by 2. And hopefully you won't have to and then multiply by 2 a second time. I think Sapling may have done that to you once. It's just kind of mean. This is an example of probably the most difficult problem you would encounter when balancing an equation. And you'll have to do at least one of those, maybe two if she's feeling froggy. But you should know how to do that because it will come up. The basic balancing and then also the type of balancing when you have to multiply everything by 2. It's kind of a pain in the butt. But if you recognize it and you know what to do with it, then you will be perfect. I am in the process of saving our participants list to make sure everybody gets credit. Time is technically up, so if you'll wait just a second to make sure that I've got it saved, I'll let you know, and I will set you free. But I've got a few extra minutes if you guys are still confused about anything. If you need any help with anything, I'd be happy to stay for a moment. Just let me get this list saved before anybody goes anywhere. Okay, list is saved, and everybody was, no, Cindy, you're fine. I saved it just now, you're in there. No worries, it happens. I saw you bouncing in and out, it happens. Everybody is saved, so you are liberated into the world, you're free. If you have any other questions, feel free to stick around. I'll hang out for just a second, but I'm gonna go ahead and turn the recording off. Thank you, everybody.